Welcome to this explainer. Today, we're embarking on a literal cosmic detective story. We are going to travel far, far beyond our own solar system to hunt down the true limits of stellar scale. We're looking for the absolute largest stars the universe has to offer, and I promise you, what we find is going to challenge every single instinct we have about size, distance, and the physical laws of nature.
To start things off, I want you to imagine something just completely wild. What if tomorrow morning, our sun simply vanished and was replaced by the biggest star we've ever found? It wouldn't just be a little hotter here. No, this new star wouldn't stop at Mercury or Venus or even Earth. Its outer atmosphere would extend way beyond the orbit of Mars, swallowing our entire inner solar system and potentially even Jupiter. All of that tucked inside a single, colossal sphere of superheated gas.
Okay, let's dive into this by setting a quick baseline. Earth feels enormous to us, right? I mean, it's our whole world. But if our planet were shrunk down to the size of a tiny marble, our sun would stand roughly as tall as a large, multi-story building. That's our baseline. Our sun is a stable, reliable, middle-aged main sequence star. It totally dominates our solar system, but on the true cosmic scale, it's about to be blown completely out of the water.
Section 1. Measuring the Giants. Finding the limits of these monsters takes some really clever work.
It's a true detective story because, well, we can't exactly fly a giant tape measure out into the void. Instead, astronomers use three incredibly ingenious steps to figure out a star's radius from what is essentially a single dot of light. First, they measure the distance using something called parallax, which is tracking how a star appears to shift as Earth orbits the sun. Second, they calculate luminosity. That's the actual, raw energy the star produces, not just how bright it looks to our eyes from Earth. And third, they measure temperature by analyzing the exact color spectrum of its light. When you combine those three clues, we can mathematically reconstruct the actual size of the star.
You know, there's a great saying in astronomy, starlight is a message packed with extraordinary detail, and the challenge is simply learning how to read it correctly, because nature rarely gives us neat, tidy lines. For these giant stars, their outer atmospheres get thinner and thinner as you go out, creating this fuzzy, glowing gradient rather than a solid, hard edge. So scientists really have to embrace that lingering uncertainty, making careful deductions to reconstruct what these distant giants actually look like.
Moving on to Section 2, the reigning champions. Let's look at the biggest stars out there. For years, the absolute, undisputed king of the cosmic giants was a star called UY Scuti. Located thousands of light-years away in the constellation Scutum, this red supergiant is estimated to be anywhere from 1,000 to 1,700 times the radius of our Sun. But here's the fascinating catch with UY Scuti. It's surprisingly diffuse. If you somehow flew a spaceship through its outer edge, you wouldn't hit a solid wall of fire. You'd actually just be entering a colossal, incredibly thin, glowing cloud of gas.
But astronomy is always evolving. And eventually, a new challenger emerged from a distant stellar cluster called Stephenson 2. Its estimated radius compared to our Sun, a staggering 2,000 times larger.
Just let the sheer reality of that scale sink in for a second. If you dropped Stephenson 218 into the center of our solar system, the giant gas planets literally become its inner neighborhood. Saturn might be its closest surviving neighbor. We're talking about an object so immense that it practically breaks our language and forces us to completely rethink what a star can actually be.
Section 3. Size versus mass. Volume versus matter. Get ready because there's a massive twist coming here.
Now, what's really interesting about this slide is how it breaks our earthly intuition. We usually think bigger automatically means heavier, right? But think of a giant hot air balloon. It has this massive volume, takes up a ton of space, but there's very little actual matter inside. Now compare that to a small, solid steel sphere. It's super compact, but it has immense weight. Stars actually work the exact same way. In the cosmos, volume absolutely does not equal mass.
As you can see, the universe offers multiple routes to extreme limits. On one hand, you've got our sprawling red supergiant Stephenson 2-18. It occupies an unbelievable amount of space, but it's basically a highly diffuse cloud. On the exact opposite hand, you have R136A1, which is a massive blue star. It has a relatively compact radius, but it contains well over 100 times the mass of our Sun. It is just unbelievably heavy and dense. It perfectly proves that the cosmos has more than one way to build a giant.
Section 4. The cosmic limits. Why do stars stop growing? What physics actually prevent them from getting infinitely larger?
Basically, every single star is locked in an eternal, super delicate tug-of-war. Gravity is constantly trying to pull the star's material inward, trying to crush it under its own sheer weight. To survive, the star generates energy through nuclear fusion deep in its core, which creates radiation pressure that pushes back outward. As long as those two competing forces are balanced, the star is stable. But as a star gets more and more massive, it has to burn vastly more energy just to fight off that crushing gravity.
And this brilliantly illustrates what astrophysicists call the Eddington limit. At a certain point, a star has to burn so intensely brightly to fight its own gravity that the outward radiation pressure actually becomes stronger than the gravity trying to hold the star together. The light literally pushes the star's own outer layers off into space. The star's extreme brilliance ends up creating instability, strictly limiting any further growth. It's a hard limit set by physics itself.
Section 5. Spectacular stellar endings. These fragile balances can't last forever.
A giant star's death is a literal ticking time bomb. For millions of years, the core continuously fuses heavier and heavier elements to keep the engine running. But eventually it hits a wall, iron. Fusing iron doesn't release energy, it actually consumes it. The entire stellar engine just stalls. In fractions of a second, gravity finally wins that eternal tug-of-war, and the core implodes at unimaginable speeds. The resulting violent rebound is a supernova. It's an explosion so incredibly brilliant, it can briefly outshine entire galaxies, violently scattering the chemical building blocks of life across the cosmos.
And the aftermath? It's a total mind-bending paradox. The enormous visible star vanishes entirely, replaced by a compact black hole. A star that used to be so huge it could swallow planetary orbits collapses down into a point where gravity is so impossibly strong that not even light can escape its pull. The universe trades unimaginable physical size for unimaginable gravitational intensity.
Section 6. The First Stars. Let's head back to the cosmic dark ages for a minute.
Because honestly, the absolute largest stars to ever exist might not even be around anymore. We're talking about population 3 stars. Picture this. Right after the Big Bang, the universe was incredibly pristine. It was basically just pure hydrogen and helium. Without any heavy elements to help cooling gas clouds fragment into smaller pieces, these ancient early stars might have grown to masses that are just flat out impossible in today's Milky Way. We're talking hundreds of times the mass of the Sun. They lived extremely fast, burned intensely, and died very quickly, seeding the early universe with the very first heavy elements.
But if we lean into theoretical physics, it takes things even further with some truly mind-bending exotic objects, supermassive stars, boasting tens of thousands of solar masses, dark stars powered not by fusion, but by the annihilation of dark matter particles in the early universe, and my absolute favorite, quasi-stars. Just imagine a massive star, but instead of a standard fusion core, it's literally swallowing a black hole sitting right inside its own center. Ideas like this completely blur the very definition of what a star can even be.
It's honestly a pretty humbling realization. Our observation has limits. Light takes time to travel across the void, and there are vast parts of the universe we simply cannot see yet. Our current record holders, giants like Stephenson 218, they are incredible, for sure, but they're ultimately just milestones on a never-ending journey of scientific discovery. The universe has had billions of years to experiment, after all.
So, I want to leave you with this question to ponder today. Have we actually found the absolute limits of nature? Or is an even larger giant still out there, just waiting to be discovered in the dark? Every single new telescope we build acts as a better lens through which we examine our reality. The cosmos is larger, stranger, and so much more extraordinary than we ever expected. Keep looking up at the night sky, because the next big discovery, it might just change everything we thought we knew. Thank you so much for joining me on this explainer.